Okay, now we're going to continue the discussion of what is the pH of. We've talked a lot about at first identifying, do I have an acid, base, or salt? And now we've added or two things. And if I have two things, for each of the things I identify, is that thing an acid, a base, or a salt? If it's a salt, I break it up into ions and I identify what each ion is. And the bottom line, basically, most of these problems will come down to, once I've identified everything, is I have two things in the beaker. One is an acid, one is a base. And the next step is to say, are those two things conjugates or are they not conjugates? In the last video, we looked at if those two things were conjugates. As you may have guessed, we're now going to talk about what if they are not conjugates. So what is the pH of a solution prepared by adding? There's lots of different ways to phrase this. Let's say 278 milliliters of 0.15 molarity nitric acid to 314 milliliters of 0.21 molarity lithium hydroxide. This is very similar to a problem that you see on your practice set. Numbers are changed. All right, so I need to have a what is the pH of? Notice that I have two things in my beaker. One of the things is nitric acid and the other thing is lithium hydroxide. And so the first thing I identify is what are they? And hopefully you recognize nitric acid is HNO3, that's a strong acid. And lithium hydroxide is LOH, and that's a strong base. And the next question you ask yourself is, are those conjugates of each other? And they're not. Remember from module, oops, I lost my thing. Remember from module 6, we learned to identify a conjugate acid-base pair. A conjugate acid-base pair are exactly the same chemical species, except the conjugate acid has an extra H plus, the conjugate base is missing that extra H plus. These are not conjugate acid-base pair. They don't match the pattern. When you decide that you have an acid and a base in your container and they are not conjugates, what you have to do, remember with the conjugates, this was a buffer problem. When they are not conjugates, what you have is you have a good old Gen Chem 1 limiting reagent problem. The first part of this is a Chem 1 concept. I have to run a reaction with these two species, not an equilibrium reaction. This is not going to be an equilibrium reaction. This is going to be a forward reaction of the type that we saw back in Gen Chem 1, where the acid and the base react completely with each other. You may recall from Gen Chem 1, an acid plus a base yields a salt plus water. All right, this is a double replacement reaction or a double displacement reaction. And essentially the way this works with the example we have here is HNO3 can be thought of as H plus and NO3 minus. Lithium hydroxide is the ionic compound, again, lithium plus, OH minus. This can be thought of as, since it's an acid, as those two. And what happens is that our ions swap. That's that double displacement reaction. That's that double replacement reaction. So the lithium ion goes with the nitrate ion. The H plus goes with the OH minus. And so I get a salt plus water. The salt is a fancy name for an ionic compound. We've seen it again here. That is the reaction between an acid and a base. If you have an ammonia type base, there's just a little bit of nuance to it. You can look up that reaction. If your base is ammonia, or if your base is an ammonia type base, a blah blah amine, you actually only get the salt. You don't get the plus water, but you do get the salt. Now, I have an acid and a base in my container. I have to run the reaction. It is a limiting reagent problem. It is not an equilibrium. Notice I did not write an equilibrium arrow. I wrote a forward arrow. This reaction will proceed until something is gone. And so what I have to determine is what's left in my container after this reaction proceeds. This is a Chem 1 concept. If you need to go back and review stoichiometry from Chem 1, do it. We can keep this in moles. Typically in Chem 1, we would keep this in moles rather than molarity as we ran our stoichiometry problems. That just makes the math a little easier. So I'm going to take these. All right, I've got 275 milliliters of 0.15 molarity nitric acid. And I've got, where am I? 300, of course, it's on a different line. 314 of 0.21 molarity. I'll just write it. 314 of, what was it? 0.21. And that was the lithium hydroxide. This was the nitric acid. Recall from Chem 1 as well as what we reviewed at the beginning of the semester, in order to calculate moles, you do molarity times volume. If you do your volume in liters, you'll get moles. And so for the nitric acid, it's 0.15 molarity, which is moles per liter, times 0.278 liters. Change that to liters. I get 0.15 times 0.278. I get 0.0417 moles. I do not want to round these values. I want to be keeping extra significant figures as I continue. And this is of my nitric acid. For my lithium hydroxide, I do the 0.21 moles per liter times the 0.314 liters. And I get 0.06594 moles of lithium hydroxide. Now, just a note, I don't mean to make this complicated, so you're welcome to ignore this. It is just as easy to work this in something called millimoles instead of moles. Millimoles. Millimoles says leave all volumes in milliliters, rather than changing to liters. If you leave all the volumes in milliliters, it just makes the math easier. You have fewer decimal places, in which case we would take the 0.15 times 278 instead of 0.278. We'd leave that in milliliters, and this would be moles per liter. So that answer would be millimoles, 0.15 times 278, and so that would get us 41.7 millimoles of nitric acid. We would take the 0.21 moles per liter times the, not the point, how about the 314 milliliters, and that would get us 65.94 millimoles of lithium hydroxide. Now when I convert back to molarity, I'd leave my volume in milliliters. So I can do everything in millimoles rather than moles. I just don't do any conversions to liters, leave everything in milliliters, and I'm going to do it that way. So these are my volumes to put in my ice table for my initial amounts. So the initial amount of nitric acid is 41.7. You can type in the 0.0417 if you want. The initial amount for my lithium hydroxide is 65.94. Again, you can type in the 0.06594 if you want to, but I'm going to leave them in millimoles. Now, this is not an equilibrium at the end. This is a final value because this is a forward limiting reagent problem. This is not an equilibrium reaction. This is a forward reaction, and it will proceed until somebody runs out. And as you can see from those initial amounts of moles and the fact that this is one-to-one stoichiometry, the nitric acid will run out first, which means we will consume that many moles of lithium, millimoles in this case, of lithium hydroxide as it proceeds in the forward direction. And so we will be left with 24.24 millimoles of lithium hydroxide at the end of this reaction. but I have to pay attention to my products. I don't have to pay attention to the water, but I have to pay attention to that salt that's formed. So I start with 0 lithium nitrate and I gain 41.7 millimoles of lithium nitrate. So I have 41.7 millimoles of lithium nitrate at the end. Once that reaction is finished, I repeat the flowchart process. I look at what's left in my beaker and I identify, do I have an acid that's left? If so, is it strong or weak? Do I have a base that's left? If so, is it strong or weak? Do I have a salt that's left? If so, break it up into the ions and identify each ion. Or do I have two things that are left? So I go through my beaker and I don't stop. I stop at what I have in my beaker. So I have two things left in my beaker. I have some lithium hydroxide and I have some lithium nitrate. I no longer have nitric acid. It was consumed in the reaction. So the two things that I'm left with in my beaker after this reaction are lithium hydroxide and lithium nitrate. And so I go through the process. Let me identify them. Well, lithium hydroxide, is a strong base, and lithium nitrate is a salt. And what do I do with the salt? I break it apart into ions, 100%, and for each ion, I identify whether it's acidic, basic, or neutral. The lithium ion comes from the strong base lithium hydroxide, therefore it's neutral. I can ignore it. The nitrate ion comes from the strong acid, nitric acid, therefore it's neutral, therefore I can ignore it. I can ignore the lithium nitrate completely because both of the ions are neutral. If I ended up with an ion that wasn't neutral, I couldn't ignore it, but I can ignore it because both ions are neutral, which means I am left with one thing in my beaker. It is lithium hydroxide. It is a strong base. And how do I find the pH of a strong base? Well, a strong base is not an acid. A strong base is 100% ionized. I break it apart to get the OH minus. From the POH, I get the pH. I do need to be working in concentration, in molarity at this point. So all I have left to do is to say, what is the concentration of lithium hydroxide? It will be the moles per liter or the millimoles per milliliter. I'm doing it in millimoles. So how much did I have left? I had 24.24 lithium hydroxide left. Remember, I am ignoring the lithium nitrate because it was neutral. So 24.24 moles. And actually it's millimoles, sorry. Sometimes I just call it moles because it works the same, divided by the milliliters in the container, and I dumped two things together. I dumped 278 milliliters and 314 milliliters together. So let me add those together. That's 592 milliliters. And so the molarity of the lithium hydroxide is 0.040945 ... molarity. Millimoles divided by milliliters is molarity. Moles divided by liters is molarity. You get the same answer. So that is the molarity of lithium hydroxide, which means the hydroxide ion concentration is also 0.40945 molarity ... which means the POH is 1.3877, which means the pH is 12.61. I can do a quick check. I had one thing in my container. It was a strong base. I am expecting a basic pH. Bam, I got it. So this problem, there are several different paths this problem can go down. But it starts with, I have two things in my container. They are an acid and a base. Once I break up all the ions for the salt and figure out what's going on there, they are not conjugates, which means it's a limiting reagent problem. And I run the limiting reagent problem. That's a Chem 1 stuff. You may need some practice. Once I finish the limiting reagent problem, I'll get a final amount. And now I look at what's in my beaker. I do the flow chart again. Now, do I have one thing in my beaker? Do I have two things in my beaker? If I only have one thing, is it an acid, a base, or a salt? If it's a salt, I break it up in the ions and I look at each ion. If it's an acid, is it strong or weak? If it's a base, is it strong or weak? If it's two things in my beaker, I identify whether or not they're conjugates. So this is the same iterative process until you get down to finally what's in my beaker. How do I work that pH problem?